Today, we're diving into one of aviation's most fascinating engineering decisions. A choice that literally keeps millions of people safely airborne every single day. And trust me, by the end of this, you'll never look at an airplane the same way again. Let's start by clearing up a massive misconception. When I say gas engine, I'm talking about the reciprocating piston engines you find in cars, not the fuel itself. Because here's where it gets interesting. Modern jet engines actually do burn a type of gasoline. It's called jet fuel or kerosene, which is basically gasoline's more refined cousin. But the way these engines burn that fuel? That's where the magic happens. It's the difference between pushing yourself on a skateboard versus strapping a rocket to your back. Both might get you moving, but one is clearly better suited for certain situations. Think about this for a second. A typical car engine has hundreds of moving parts. Pistons pumping up and down, valves opening and closing, a crankshaft spinning around. It's like a mechanical orchestra where every instrument needs perfect timing. Now imagine trying to conduct that orchestra while flying through a thunderstorm at 500 miles per hour. Starting to see the problem? Here's where we need to talk about something called the altitude problem. Lighting a match at sea level is much easier than lighting a match at the top of Mount Everest. Why? Because the air up there is about 1/3 as dense as it is down here. Your car engine faces the exact same problem. Piston engines are like that friend who can only function with their morning coffee, except their coffee is oxygen. They need a very specific mixture of fuel and air to work properly. At sea level, no problem. But climb to 30,000 feet, and that engine is basically suffocating. Commercial airliners cruise at altitudes where the air pressure is so low that water boils at room temperature. Your car engine would wheeze, sputter, and die long before reaching those heights. Meanwhile, jet engines actually love thin air. They're designed to compress massive amounts of air internally. We're talking about compression ratios that would make your car engine explode. A modern jet engine compresses air by a factor of 40 to 1. It's creating its own atmospheric pressure, basically bringing sea-level conditions with it wherever it goes. Here are some numbers that will blow your mind. A typical car engine produces about 0.5 horsepower per pound of engine weight. Not bad for getting you to work and back. But a modern jet engine? We're talking about 6 to 8 horsepower per pound. Imagine if your 300 horsepower car engine suddenly had 3,600 horsepower but weighed the same. That's the kind of power density we're talking about. It's like comparing a household fan to a hurricane. Here's a real-world example. The General Electric GE90 engine, which powers Boeing 777s, produces 115,000 pounds of thrust. Converting that to horsepower at cruising speed, we're looking at roughly 100,000 horsepower. From one engine. That's more power than 100 Formula One race cars combined. Now imagine trying to get that same power from piston engines. You'd need an engine the size of a building, and your plane would look less like an aircraft and more like a flying warehouse. Not exactly aerodynamic. But here's the kicker. It's not just about raw power. It's about sustained power. Your car engine might produce peak power for a few seconds during acceleration, but a jet engine maintains enormous power output for hours on end. It's the difference between a sprinter and an ultramarathon runner who can sprint the entire race. This might sound counterintuitive, but jet engines are actually simpler than car engines. I know. How can something that costs millions of dollars be simpler than what's under your Honda's hood? Let's break it down. A car engine has pistons, connecting rods, a crankshaft, camshafts, valves, valve springs, timing chains, and dozens of other reciprocating parts. Each part moves back and forth or up and down thousands of times per minute. Every direction change is a stress point, a wear point, a potential failure point. A jet engine? It basically has one moving part, a shaft with compressor blades on one end and turbine blades on the other. Everything spins in one direction, continuously, smoothly. No reciprocating motion, no complex valve timing, no distributor caps or spark plug wires to worry about. It's elegant in its simplicity. Leonardo da Vinci would have loved it. Maximum efficiency through minimum complexity. Think about it this way. What's more likely to break? A ceiling fan that spins continuously, or a sewing machine with all its intricate back-and-forth motions? The jet engine is the ceiling fan of the aviation world. If ceiling fans could generate hurricane-force winds and run for 20,000 hours between overhauls, here's something you've probably never thought about while flying. Vibration can literally shake an airplane apart. I'm not trying to scare you. Modern planes are incredibly safe. But vibration is an engineer's nightmare at 35,000 feet. Piston engines are vibration machines. Every time a piston fires, it's like a tiny hammer blow. In a six-cylinder engine running at 2,500 RPM, that's 7,500 little explosions per minute. Each one sends a shockwave through the engine mount, through the wing, through the fuselage. Over time, this can cause metal fatigue, loose rivets, and cracked components. Now multiply that by the 4, 6, or even 8 engines you'd need to power a large aircraft with piston power. It would be like strapping a paint shaker to each wing and hoping for the best. Jet engines, on the other hand, run smooth as silk. The combustion is continuous, not pulsed. The rotation is balanced and constant. Passengers can place a coin on edge on their tray table and it'll stay standing during cruise flight. Try that in a propeller-driven aircraft with piston engines. That coin would dance off the table faster than you can say turbulence. This isn't just about comfort. Reduced vibration means less maintenance, longer component life, and most importantly, better safety margins. When you're 7 miles up in the sky, you'll want everything running as smoothly as possible. Let's talk about speed, because this is where piston engines hit a brick wall. Literally, an aerodynamic brick wall. Propeller-driven aircraft with piston engines face a fundamental problem. Propeller tips can't exceed the speed of sound without losing efficiency dramatically. As a propeller blade approaches sonic speed, it creates shock waves that destroy lift and create enormous drag. It's like trying to swim through molasses instead of water. This limits piston engine aircraft to about 400 to 450 miles per hour max. And that's pushing it. Most cruise much slower, around 200 to 300 miles per hour. Meanwhile, jet engines laugh in the face of the sound barrier. They're designed to handle supersonic airflow. The Concorde cruised at Mach 2, twice the speed of sound. Modern commercial jets cruise at about 550 miles per hour, just under the sound barrier. Not because they can't go faster, but because going faster isn't economically efficient for passenger travel. Here's a mind-bending comparison. A flight from New York to Los Angeles in a modern jet takes about 5.5 hours. In a fast piston engine aircraft, you're looking at 12 to 15 hours minimum with multiple fuel stops. That cross-country business trip just became a 2-day adventure. This might shock you, but jet engines are actually more fuel efficient than piston engines for their intended purpose. Wait, what? How can something that burns thousands of pounds of fuel per hour be efficient? It's all about the right tool for the job. Sure, a jet engine burns more fuel per hour than a piston engine, but it's also moving 300 people at 550 miles per hour. Do the math on fuel per passenger mile, and suddenly jets look pretty good. Modern high-bypass turbofan engines are marvels of efficiency. They move huge amounts of air at relatively slow speeds, which is far more efficient than moving small amounts of air at high speeds. It's the difference between fanning yourself with a newspaper versus blowing through a straw. Which one moves more air with less effort? At cruising altitude, where the air is thin and drag is reduced, jets can achieve fuel efficiency that would make piston engines jealous. We're talking about 100-plus passenger miles per gallon in some modern aircraft. Your car probably doesn't even get 100 passenger miles per gallon with just you in it. Plus, jet fuel has more energy per pound than gasoline, and jets can carry enormous amounts of it without the complex fuel management systems piston engines would need. No carburetors to adjust for altitude, no fuel pumps struggling against vapor lock, no concern about fuel mixture ratios. The engine takes what it needs and burns it completely. When you're flying over the Pacific Ocean, thousands of miles from the nearest airport, engine reliability isn't just important, it's everything. This is where jet engines absolutely demolish piston engines. Modern jet engines are so reliable that twin-engine planes are certified to fly up to 5.5 hours away from the nearest airport on a single engine. That's called ETOPS, Extended Twin Engine Operations Performance Standards. And pilots joke it stands for engines turn or passengers swim. The mean time between failures for a modern jet engine is measured in tens of thousands of hours. Some engines go their entire service life, 20,000 plus flight hours, without a single in-flight shutdown. That's like driving your car 1.2 million miles without the engine ever failing. Piston aircraft engines? They require overhauls every 1,500 to 2,000 hours. That's like rebuilding your car engine every 90,000 miles. And in-flight failures, while still rare, are orders of magnitude more common than with jets. The key is that jets have fewer failure points. No magnetos to fail, no carburetors to ice up, no valve trains to break. Just smooth, continuous rotation with built-in redundancy. Each engine is actually multiple engines in one. If a turbine blade fails, the engine keeps running. Try running your car with a broken piston and see how far you get. Here's something wild. Jet engines actually run hotter than piston engines, but they handle it better. The combustion chamber in a jet engine reaches temperatures over 2,000 degrees Celsius, hot enough to melt the engine itself. So why doesn't it melt? Engineering genius, that's why. Jet engines use sophisticated cooling systems where air flows through tiny holes in the combustion chamber walls, creating a protective buffer of cool air, still hundreds of degrees, but cool by comparison. The metal components never actually touch the hottest gases. Piston engines can't play this game. They rely on physical contact between pistons and cylinder walls, with all that friction and heat buildup. They need complex liquid cooling systems with radiators, water pumps, and thermostats, all potential failure points. And at high altitude, where the air is thin, cooling becomes even more challenging. Jets actually use their extreme temperatures to their advantage. The greater the temperature difference between intake and exhaust, the more efficient the engine. It's basic thermodynamics, the Carnot cycle, if you want to get technical. Piston engines are limited by the temperature their metal components can withstand in direct contact with combustion. The gap between piston and jet technology is only getting wider. Modern jet engines are incorporating ceramic matrix composites that can withstand even higher temperatures. They're using 3D printed components with internal cooling channels impossible to manufacture traditionally. They're adding geared turbofans that allow different sections to spin at optimal speeds. Meanwhile, piston aircraft engine technology has barely changed since the 1960s. Sure, we've added electronic ignition and fuel injection, but the basic design would be recognizable to Charles Lindbergh. The next generation of jet engines will be even quieter, more efficient, and more powerful. Some experimental designs are achieving bypass ratios of 15:1 or higher, meaning 15 times more air flows around the engine core than through it. That's like having a propeller's efficiency with a jet's power and altitude capability. So there you have it, the fascinating truth about why planes don't use gas engines. It's not just one reason. It's a perfect storm of physics, engineering, and practical requirements that make jet engines the only sensible choice for modern aviation. Ready for takeoff? Because now you know exactly what's powering your journey through the skies. Now that you know why planes don't use gas engines, do you think we'll ever see fully electric passenger planes take over? Drop your thoughts in the comments and don't forget to like and subscribe.